Quantum tunneling is a quantum mechanical effect that occurs when a particle moves through a barrier that it ideally should not be able to surmount. iStock scientists have figured out a way to generate electricity from the Earth's surplus infrared radiation and waste heat, using quantum tunneling. Our planet absorbs massive amounts of sunlight, which in turn leads to a near-constant emission of infrared radiation, which is estimated to amount to millions of gigawatts of energy. Quantum tunneling is a quantum mechanical effect that occurs when a particle moves through a barrier that it ideally should not be able to surmount. For example, in classical physics, a ball rolling up a hill would require a certain amount of energy to get up the hill and to the other side. However, in quantum physics, the ball could dig through the hill with less energy, in effect tunneling through the barrier. Researchers believe this infrared heat can be harvested 24 hours a day to generate electricity, using quantum tunneling. The process involves the use of custom-designed antennas that are capable of detecting infrared or waste heat as high-frequency electromagnetic waves, converting these quadrillionth of a second wave signals into electricity. Since infrared emissions have very small wavelengths and can oscillate thousands of times faster than a typical semiconductor capable of moving electrons, they require nano-antennas, which can be difficult to create or test. However, according to scientists behind the new study, quantum tunneling can provide the breakthrough required to achieve the goal. There is no commercial diode in the world that can operate at such high frequency. Atif Shamam, the lead researcher of the new study, from the King Abdullah University of Science and Technology, KAUST, in Saudi Arabia, said in a statement. That's why we turn to quantum tunneling. Tunneling devices such as metal insulator (MEM) diodes transform infrared waves into current by moving electrons through a nanometer-thin barrier. In order to generate the intense electrical fields needed for tunneling, the researchers created a bow-tie-shaped nano-antenna, sandwiching the thin insulator film between two slightly overlapped metallic arms made of gold and titanium. The most challenging part was the nanoscale overlap of the two antenna arms, which required very precise alignment, Gaurav Jaiswal, a postdoctoral researcher involved in the research, said. Nonetheless, by combining clever tricks with the advanced tools at KAUST's nanofabrication facility, we accomplished this step. The MEM diode created by the researchers was able to successfully capture infrared radiation with zero applied voltage, a feature that enables the device to be switched on only when required. The research has been published in Materials Today Energy.